All right, so we're answering some homework questions from your work with reviewing systems and some new systems too. And we're on worksheet. Come on, buddy. Any day now. Worksheet 4. I'm just trying to like delay so my computer will work. There we go. All right. So worksheet 4, number 14. It just didn't work out, Piper? What method do they want you to use on this section? Does it say? Elimination method? Okay. It's probably a negative sign issue. That's usually what the issues are. Who did you try to eliminate? Okay. Did you find a common multiple that would work for an 8 and a 10? You just used 80? Okay, that's fine. So they already have opposite signs, so you don't have to mess with signs at all. So you could just do, whoops, that's an 8. Did anybody use a different common multiple besides 80? What'd you use, Brandon? 40 would work, yep. There's a lot of things that would work. You just have to find a common multiple. And Piper uses my favorite method of just like swap the numbers, and then it's always a multiple, which is nice. You do kind of end up with large numbers, though. Okay, so it could be a negative issue, Piper. The other issue that people run into is they forget to multiply this back number by the 10 and by the 8. Do you think that's what happened in your work? Okay. So we end up with a negative 80x and a minus 70y equals 140. And then an 80x plus 90y. A little calculator help on this one? Is it negative 96? No, it's not. It's not that. What is it? Oh, okay. That's way off. I'm dozens of numbers off. I can't multiply right now. Help!
128.
Thank you. Negative 128. Did you write down a negative 16 or just something wrong? Oh, bummer. Well, that'll do it. All right, I think you can take it from there. Yes, ma'am. What else? Great. I can already tell you where this went wrong. The distribution of the negative. Did you forget to distribute the negative to the 3y and the 3x and the 3? No? Okay. Let's find out. Usually that's like exactly where it went wrong for kids, and they go, oh, man. All right, so the first thing you had to do on number 22 was solve for one of the variables. I'm hoping you solved for the bottom equation's y value, Cheyenne. Is that what you did? Okay, so you got 3x plus 3 as your formula. Okay, so this is what we're plugging in for all of the y's. So your formula starts off with y squared. So we have a little FOIL problem right off the bat. And then plus 21x minus y in quantity parentheses plus 30 equals 0. So plugging in the 3x plus 3 to both places. These are just so easy to mess up. That's why they're frustrating. Yes, sir?
It just says solve. Can I solve it by any means I want?
On your homework, yes, but I would probably, I don't think it does say that.
But unless it specifies by which...
It will always specify. Is that your question? Is that your true question?
Yeah.
The only time it won't specify...
Says solve, so I was just curious.
Well, that's because you only have one method to solve these. You don't know how to do these any other way.
I'll eliminate them.
You can't. You don't know how. All right. It sounds like a challenge, doesn't it? All right, so this is 9x squared plus 18x plus 9 when you FOIL that guy out. Is that possibly where the mistake occurred? She's like 4 years ahead of me. Is this where it happened? This is that FOILed out. Yeah. All right. I gotcha. All right. So unfortunately, that does cost you quite a bit, right? This is usually where the mistake happened. I kind of thought it would be right here, but you said no, so good for you. Oops. I'm just switching colors for no reason. This is probably where I'm going to leave you. You have a lovely quadratic. It'll have a common factor. It is lovely. It's going to come out quite nice, actually. What? Now, there's only one solution to this one. So, that's exciting.
That's lovely.
Yeah. I thought so. 23 has more solutions. So is 21. Yes, ma'am. Sure. Oh, the old current in the boat. All right. 24 is a boat in the water question.
Oh, we love those.
We love these. All right, so a boat travels 96 miles downstream and back. I think the way they word that is a little ambiguous. It's 96 miles down, and then they turn around and come another 96 miles back. So downstream took 6 hours. Coming back, it took 12 hours. So downstream is the faster one, so they're going with the current. So we need to set up some variables, Sky. What do you want to use to represent the speed of the boat when it's not being pushed by the current?
Yes.
Oh, jeez. I'm going to go with B. Thanks, Sky. It's the speed of the boat. And then what would you like to use to represent the speed of the current?
W.
Just got to be weird, huh, Daniel? All right, speed of the current.
C. I was thinking for water. It wasn't just I wasn't just pulling W.
Okay.
It was weird.
All right. I would like to see little pictures of tiny sailboats on everybody's picture next. You can use pictures for variables. Did you know that? It'd be fun. Okay, so distance equals rate times time is the setup that we need to come up with for this problem. And the distance, I believe we know, isn't that 96? So downriver and back. Those are the two equations you're going to set up for me. So downriver, they're going a distance of 96 miles. But if you think about going downriver and it's the faster trip, how fast is the boat going? Because it's not just going B.
It's going B2.
B plus W.
Oh.
So however fast the boat is, like, you know, set to go, I'm assuming it's a boat with a motor, plus the speed of the water current. So that's the rate, and then how long did that trip take? How many hours? Be a 6-hour trip. And then on the way back, still 96 miles, but now how fast is the boat going? So it was programmed to go, yeah, instead of B, now it's going to be minus W, because they're being hindered by the water current. And then times 12, yep. So your next step is for you to kind of clean this up, distribute the 6 and distribute the 12. And I'm probably going to leave you after this step, okay? So you got a little equation, a system of equations to solve. I think elimination would be a fine choice here. I personally would eliminate the W's because they already have opposite signs, but it's up to you.
What?
The W's already have opposite signs.
Oh, they do.
So once you find one of the variables, Sky, plug it back in and find the other variable. You got this. Any other questions on your homework?
Wait, but never mind. I was thinking that, but these also.
Sure. 17. You got a weird solution and you weren't sure what to do with it? Well, oh, it's way not in the right order. You gotta rearrange things, huh? Okay. Did you have 96x minus 32y equals negative 58? You do now. That could have been the problem right there. And then you would have had 126x minus 42y equals negative 84. Oh. Well, do that rearranging. I think I'm going to use the Piper method, where I just multiply them by the other number. Because I don't even care to find a least common multiple on those guys. So, like, if you chose to... like, for instance, if you wanted to eliminate the x's, you could multiply that top equation by, like, negative 126 and the bottom equation by 96. And that's definitely not the least common multiple, but, like, I don't care. What is it? That's not. Did you divide by stuff? Um, 16 on both equations, though? That wouldn't be a common multiple. You might have multiplied one of them by 16 and one of them by something else. Yeah. Something else. We're not sure what. The point is, if you can't find the least common multiple, you can employ what I'm now going to refer to as the Piper method, which is also the Abruzzo method, because we're both lazy. Piper, sorry. And just multiply by the other one's number. In hindsight, the y's are a little smaller. I'd probably go with the y's, but whatever. I don't want to do that one for you because something cool happens at the end and I want you guys to figure out why you have it. I think you got it. Alright. Find worksheet 6. That's our notes for today. We're going to talk about our friend, the Matrix.
Like the movie The Matrix?
Nah, actually, yeah.
It's a good movie.
Yeah, well, there are mini math applications and theories that go along with the movie The Matrix. Probably would have been a really cool thing to watch today. Too bad it's rated R and we can't.
You just have to get past. You know, bad stuff only happens in the third one. So.
I feel like your definition of bad stuff is a little skewed right now.
What do you mean? Well, I mean, like, people die and stuff. But...
Jeez.
Not that bad.
So cutthroat. Okay.
The third one's got naughty stuff,
Once we get into more of the Matrix chapter next week, we'll discuss like actual like true life applications of matrices, and there are a lot. But for now, we got to do the boring work of how to handle a matrix, what to call a matrix, what are the dimensions of a matrix. So for now, just open up to worksheet 6, and you're going to take a couple of notes at the top. But we're going to do everything today without a calculator for a few reasons. 1, the problems I give you are simple, and we should be able to do them without a calculator. 2, no calculator for portion of the SAT test. We got to get ready for that. And 3, many of the questions we give you in PreCalc have algebraic components to their matrices, so you can't use a calculator. So some of you took college algebra last year, and you're like, I only do these on the calculator. Well, not today. Today you're going to do them by hand. All right, so first thing we have to recognize on a matrix is that they're a way to set up systems. Usually they're coefficients to equations, and they represent data values, but matrices are used a lot in like pricing and creating like cash register programs, and how do you mass take discounts, and how do you mass apply tax? You know, these are all matrices, and they're programmed that way. They have rows and columns in the matrix. Rows measure horizontally, and columns measure vertically. So you don't have to write this one down, guys, but just on my board here, this particular matrix has 2 rows. This is not on your paper anywhere. And it has 3 columns. So the dimensions of this matrix would be known as 2 by 3. Not to be confused with 3 by 2. A 3 by 2 would look completely different. It would have 3 rows and 2 columns. Okay? So the dimensions are really important because that's what allows you to do and perform the operations and whether you can add or multiply them together. Also helps you with the resulting matrix. Now, this is a little thing they used to have to tell us to remember how the dimensions of a matrix are listed. They said, remember RC Cola. I don't even know if RC Cola is a thing anymore.
Yes, it is.
Is it? Oh, my apologies to RC Cola Company.
RC is amazing.
Okay, well, Daniel says it is, and it's okay. So you will remember this. If you guys forget, oh, is it rows by columns or columns by rows? Well, it's RC Cola. That's how you're supposed to remember it. The little trademark symbol. I didn't do that, so good on them, whoever did it.
They really feel it.
All right, next thing I got to talk to you about on a matrix is every one of those digits that was within the matrix has a position value. So like this first one, this is position 1, 1. They wrote it with subscripts, but what you'll often see in your textbooks is like 1-1. That means it's in row 1, column 1. That's what that means. So this guy, which they'll often write as 1-2, means it's in row 1, column 2, and so on and so on. So when I rattle off a matrix to you, you usually start at 1, 1, and you start reading it over to the right, and then you jump down to the second row, and you jump down to the third row, and so on and so on. All right, lots and lots of applications coming your way next week. Today we're doing the boring stuff. So now you're on worksheet 6, and I want you to write down the dimensions of the matrix just so we can get practice identifying the dimensions. So you can only add and subtract matrices together if they have the exact same dimensions, and then the resulting matrix will have those same dimensions as well. So this matrix right here is 1 row by 2 columns, and so is this one. So the dimensions are 1 row by 2 columns, which means my resulting matrix will also be 1 row by 2 columns. So what I like to do is write the matrix out with little empty spaces waiting for my answers. And then without any instruction, you guys probably would have got this right. You're just going to add the components. So 6 plus 3, better known as 9. And then in position 1, 2, you have -2 plus 1, better known as -1. So that would be a really easy question that I probably will never ask you because that's too easy for PreCalc. But I will totally ask you something like number 2. Now, first of all, what are the dimensions? I see that they're the same size matrix. I just want to know how to write my answer down. It's a 2 by 3. Very good. So my resulting matrix will also be a 2 by 3. So go ahead and give yourself a 2 by 3 skeletal setup. And then, ironically, I really messed this problem up first hour after I just warned them to be careful on how they subtract. And then I proceeded to subtract wrong like 3 out of the 6 numbers. Okay, so be better, Abruzzo. You got a -1, and remember you're subtracting -6. -1 minus -6 is a 5. According to most people, just not me, apparently. All right, same idea, guys. 2, you're subtracting a -5. 2 minus -5 is a 7. -4 minus 3 is a -7, right? Down here, now we're in row 2, column 1. So -4 minus -2 is -2. Thank you. I almost wrote down the wrong answer. I told you I'm cursed on this problem. Okay, next one. -3 minus 6, -9. And 1 minus 4. What? You really had me going for a minute.
What?
I don't know.
What did I do?
You did what I do, is you look at the wrong number. Like, literally, the time it takes for my eyes to travel from one matrix to the other, like, I've forgotten what number I'm subtracting. It's awful. Just know, Daniel, that it's an us problem. No one else does this, I guess. They all scoff at our mistakes. Okay, here's why we got to understand matrix operations, because I'm going to give you something like this. Now, first of all, little notational issue. Some kids don't realize what's going on. This matrix is a 1 row by 3 columns. Those are the 3 values right there. As is this one, 1 row by 3 columns. So your resulting matrix will also be a 1 row by 3 columns. So, got some algebra fun going on here. Remember that you are subtracting 4zx minus 2y. I think that's a fine answer for that value, yeah. There's really nothing you can do. You could flip the order of z and x around if it bothers you, but I don't really care. All right, similarly for position 1, 2. Careful on this one, guys. You've got a -3x, and then you're subtracting y plus 5. And you got to subtract everything and distribute. So you're subtracting y, and you're also subtracting a 5. I wrote too big, so I have to go diagonal. And then you have x minus 5z, and then minus a -1. This is another place I screwed up last hour, so that's a +1. That, my friends, is your resulting matrix.
Ugly.
Or is it? Beautiful.
No, it's ugly.
You got to learn to see the beauty in the algebra, man.
It's ugly.
So, this matrix is a 2 by 3. And clearly this matrix is not. So this is a 1 by 4.
So we do NA.
So you say 2 things. You can either say that this is undefined, meaning you cannot perform the operation, or you can write DNE for does not exist. There is no resulting matrix that exists. Don't write no. That doesn't mean anything.
Simplified, right? Undefined.
And he writes no. No. All right, scalar multiplication. I probably could have had you guys get the next question right without giving you any insight as to what to do. But what we're going to be seeing on our homework and eventually our test next week is scalar multiples are used quite a bit when you want to do like a mass increase or decrease in a series of values. So like if I wanted to curve everybody's grade and I wanted to give you all like a 5% boost, like I could, technically the gradebook is a giant matrix. So they have a capability of me being like, bump everybody by 5%. Boom! I'm not going to do that. It's too much. You got to earn your PreCalc.
What do you mean? It's not too much work, though, because you just say...
No, it's not too much work, but it's 0 work for you, and that makes me feel icky.
No, well, okay, yeah, I'll go onto your computer.
You know, I can easily also decrease your scores, mass.
You know, I don't think we need... I don't think we need your stats, okay?
Wow. Okay, so I could increase all quiz scores 12%. Now, for everybody, that's a different value, right? I don't mean like 12% from the class average. It's your percentage increased 12%. So I could basically import a program to do that. The gradebook is set up that way. It is a giant matrix, so that's kind of cool. So here's some very boring examples. Number 5, what do you think they want you to do here?
Multiply.
Yeah, it's called a scalar multiple. Write that down in your notes.
How is the gradebook a giant matrix? Are you saying because it has... Like,
Every computer program is a matrix. It's coded in matrices. It's kind of amazing. Yeah. It starts off as a matrix. Eventually it goes into code and the language is a little different looking, but yeah. So like a gradebook in particular or anything with accounting, Excel, for instance. The cells that you put into Excel are technically set up in matrix form. So like when you take cell A2 and you command it to multiply by whatever, and then you drag that formula down like you can do in Excel, it's performing those operations in a matrix form is what it's doing. I love Excel.
Excel? I hate programming Excel.
Oh, do they make you guys do? I think we talked about this. They do have you do Excel a little bit in some of your classes, right?
Yeah. You,
I feel like they should do more of
they
that.
require,
Or
they require
at least
you to
Google
take
Sheets a little more.
A computer.
Some computer thing and you do some.
Yeah.
Yeah.
A computer technology.
Excel's kind of
I
awesome.
did intro to engineering design and accounting, and we did nothing in that class except not what we were supposed to. Except now we're.
Okay, so we're going to multiply everything by a 3.
Yep.
So your resulting matrix looks the same as far as dimensions, but now all the values are different. It's a -6, it's a 9, it's a -3, and it's a 3. I don't think I'd even teach that to you. I think you would have figured it out. 6 is interesting because it looks like, oh man, there's 2 things I got to do. I got to do a scalar multiple and then I got to subtract. But wait, Adam's going to write no. Because why?
Can't do.
This is undefined. You cannot subtract these 2 matrices because they don't have the same dimensions. If you don't like to write undefined, you can write does not exist by abbreviating it DNE.
Or make it even smaller and write
I'm going to write no on your test. I just want you to know that. And it's not going to be a happy no. It's going to be a mad no. All right, number 7. I don't know. What do you think? I don't even want...
No.
I'm just writing no on all these. No, we can do this. So think of it like an equation. Forget this for a minute. If you just had to solve for y, what would you do? You would divide by -3. Can you just do that? Yeah. So this becomes a -1, a -4, a 7, and a 7. So this is matrix Y. If you were to go back and plug it back into the statement and multiply it all by a -3, you'd get this guy as a result.
I understand.
Okay.
I was really confused because it was like you couldn't multiply by matrices that aren't the right dimension.
Right, but a scalar factor is not a matrix. Right. That's a good question.
That's
yes.
why I was confused.
So these are the kind of questions they like to throw on standardized tests because a child who really doesn't have a lot of knowledge about matrices can kind of figure out what they want you to do, even though you don't really know if you're certain to be right. So like this particular one, there's a mystery matrix here. And when you add it to 106, you get this as an answer. So let's talk about what this matrix needs to be. Well, it needs to be the same size. So 1 plus mystery number gives you a 5. Daniel's thinking a 4. Yeah. And then 0 plus mystery number has to give you a -3. So -3. And then 6 plus mystery number gives you a 7. So that'd be a 1. So it's not like crazy math we're doing. They're just the idea that you're setting up your math in a matrix is just organizing your information. That's all it's really doing. It allows for easy calculation in the future. I know you don't believe me yet because you're like, this doesn't seem easy at all. It will be. Okay. Multiplying matrices by hand. First thing you got to do when you're multiplying matrices is determine whether or not you can even multiply them to begin with. So what you have to do is figure out the dimensions of the first matrix and compare them to the dimensions of the second matrix. And this is the few times in math where multiplication order does make a difference. So if I tell you A times B, that is not the same thing as B times A in matrices. So like this example, which is not on your notes anywhere, this particular matrix A, this is a 1, 2, 3, 4 by 2. And then matrix B is a 2 by 3. So the first thing you'd have to do is kind of write their matrices dimensions side by side like that, and you check the inside's dimension. If these match, that means yes, you can proceed. And then the outer dimensions, these are the dimensions of what's going to be called your resulting matrix. So when you go ahead and multiply these two guys together, the resulting matrix is going to be a 4 by 3. So your first job is to identify the dimensions, check if you can even do the operation, and then tell me what the result looks like. So, I'm going to skip to your notes here. All right, let's talk about dimensions, guys. This
No.
guy is a 2 by 3. This guy is a 3 by 1. So my first question is, can you even multiply them together? And the answer is yes, which is sad news, frowny face, because that means I have to do work. Now, what are the resulting dimensions? Yes, my result is going to be a 2 by 1. So what I'm going to do is I'm going to write kind of a large matrix with 2 rows and 1 column. And you're going to be like, why is that so large? And you'll see why in a minute. Okay, if you have 2 colors, now would be a great time to bust them out. And with your first color, you're going to circle the rows from your first matrix. And with your second color, you're going to circle the columns from your second matrix. There only happens to be 1. Oops. All right, so this first cell in the matrix, this is row 1, column 1. So what we do is we take row 1 from the first matrix and column 1 from the second matrix, and we multiply their pieces together while also simultaneously adding them together. So this is what that looks like. 0 times -4 is a 0, plus 2 times 0 would be a 0, plus -4 times 5 would be a -20. I'll clean that up in a minute. All right, we're going to do the same thing here, but this time we're in row 2, column 1. So you take row 2, multiply it by column 1, and you get 4 times -4, which is -16. -4 times 0 is 0. And then plus 30. 6 times 5 is 30. So once I clean up that matrix, the position 1, 1 comes out to a -20. And position 2, 1 comes out to a 14. There's your resulting matrix. That was a fun time.
Yeah.
And those of us who took college algebra already realize that, yes, you can multiply these on your calculator. The actual action of multiplying them is very easy and quick. What's annoying is having to edit the matrix every time. It would take you a long time to edit these matrices every time you did these problems, and it's not a time saver at all. Well, we will go over it again because we are going to have some large and in-charge matrices in the future where we do want to use our calculator for sure. This just isn't one of those cases. Also, on number 10, I believe I changed the problem. Didn't I throw this and make it a B? Haha! So now, those of you who are like, I don't care what you say, I'm using my calculator. This is where I'm going to get you. You have to use your brain on this one.
Well, that looks like a 6 to me.
It's a B. It says this is the letter B.
Not on mine.
It says right here. All right, so first thing we got to do is check to make sure we can even multiply these together. So the dimensions of this first matrix are a 2 by 2. This guy is also a 2 by 2. So the inside dimensions tells us that, yes, we can multiply them together. And the resulting matrix is a 2 by 2. So I kind of write really large matrices at first so I can write out my work, especially in my notes when I need to write down how I even got these numbers. Okay, if I have 2 colors, this is where I bust them out. I circle the rows from your first column, always the rows from the first column. Rows from the first matrix, goodness. And then the columns from the second matrix. Hello, misspeak. Alrighty, here we go. So this first position, this is row 1, column 1. So you're taking row 1 and column 1. Here we go. -18. And then minus 5b. You can say plus -5b, but that's also minus 5b. Whew. So that was row 1, column 1. All right, I'm going to move over to position 1, 2. This is still row 1, but now it's column 2. So 6 times -6 is -36. And then plus 25. All right, so now we're going to do row 2, column 1. So that would be a -3 and then plus 3b. And now we got row 2, column 2. So that's a -6 and then a -15. You could say plus -15, that's fine. All right. So clean this up as best you can. Some of them do not clean up. For instance, -18 minus 5b is just that. negative 36 plus 25 is a negative 11. Negative 3 plus 3b doesn't clean up. You can reverse the order if it bothers you, but I don't care. And then negative 6 minus 15 is a negative 21. Whew, lovely. That was just glorious, wasn't it? All right, flip around. Check your dimensions before you get going. This is a 3 by 2. And this is a 1 by 2.
No.
So, if I check the inner dimensions, you guys keep telling me no. What you really should write down is either does not exist, or you can say this matrix would be undefined.
Can we pretend that this one is worthy of it and make 12 not worthy of it?
You're not excited about 12? Scared of a little algebra?
Right.
Me too. All right, let's take a look at number 12, because Daniel already told me that we can totally multiply these together. This is a 3 by 2, and this is a 2 by 1. Okay. So the fact that the inner dimensions match, that means you can multiply them. And then the resulting matrix is a 3 by 1. So, make a pretty large and in-charge 3 by 1. All right, start circling. I need the rows from your first matrix. And then there's only one column in the second matrix, so that's it. And yeah, there's a lot of algebra in here, guys, but that's okay. We got this. We're in PreCalc. Here we go. Negative a times negative 6b would be a positive 6ab. If you wrote ba, it's fine. Plus 4 times ba would be 4ab. And yes, that does simplify, but I'm going to hang on till the next step to actually go through simplification. All right, now let's take the second row with the column. That's a positive 12a squared b. Yes, Brandon? Okay. And then this next part, plus, oh boy, that'd be a to the third b. A squared times ba. Yeah? You guys got me paranoid now. When I multiplied a squared times ba, I got a to the third b.
Sure.
That was very patronizing. Wait, what? Is it not okay?
Yeah. What did I do?
I don't know.
I don't know what I did.
Okay.
Whatever I did was wrong.
Okay. Well, you know, can't always be right. And then this last row with the column, let's see, that would be a 30b. And then plus ab. So, good news, bad news. Not quite done, but the good news is the only thing you have to finish is that top entry value there. That just simplifies to a 10ab. So, if you don't mind, I'm just going to do this. Now we're done. Well, that was just lovely. Huh. You didn't like that? Well, you're not going to like this next part either, then. All right. This part's actually fine. So what we have here is we had a matrix, and then they asked me to find the determinant of the matrix. So here's, first of all, how I know they want me to find the determinant. The directions say evaluate the determinant. The second reason I know it's a determinant is because of the notation. You notice how these look like absolute value bars? When you have what look like absolute value bars surrounding a matrix, this is called a determinant. So the formula for the determinant is diagonal 1 minus diagonal 2. So you might be wondering, well, which one's diagonal 1? It's what I call the left diagonal. So this guy right here is diagonal 1. And you're going to multiply those babies together. So negative 2 times 3 is negative 6. And then you're going to subtract from it the value of diagonal 2. So this guy, you guessed it, is diagonal 2. So that's a negative 10. And then when you simplify negative 6 minus a negative 10, that becomes a 4. The value of this determinant is a 4. So your calculator, well, we use determinants to find inverses. I'm going to show you that one next. Your calculator has a way of finding determinants, but 2 by 2s are so easy that we should just do them by hand. They're really quite easy. Less easy. And we won't be doing them by hand. Trust me, you don't want to do that one by hand. All right, didn't I add an algebra component to this one? So an A. Ah, cool. All right, so same formula, diagonal 1 minus diagonal 2. So here's diagonal 1. What, that's a negative 6? And then we're going to be subtracting diagonal 2, which we changed a little bit to be 4a times 3, so 12a. And there's no simplifying you can do there, guys, so the value of your determinant on that particular one is just that. So then the great question was asked, why do we need to calculate a determinant? Is because of, there's no thing here, I gotta find it. Okay, because of the next question. It says find the inverse of the matrix. Okay, so I don't have a slide for this one. This is number 15 in your notes. The original matrix is this, 2, 3, 1, 2. And essentially, I will be asking you guys to find inverses, but I'm probably just going to ask you to use your calculator, because even I don't remember this formula. It's not that I don't remember it, I screw it up. So there's two ways to find matrix inverses. The first way is the way I would do if I was a student and I was forced to find them by hand. Okay, so the original matrix on a 2x2, the position names are A, B, C, D. So kind of jot this down somewhere on your paper. An original matrix would just be A, B, C, D, like that. The inverse matrix is 1 over the determinant times, now this is where it gets kind of weird, the A and D switch. So D comes first and A is in the end. And then the other thing that changes, C and B stay where they're at, but they negate. So it's negative C and negative B.
Whoa.
So this is essentially a shortcut to the other way to finding inverses, which I will show you the other way because we're going to have time to do it. Okay. So this question, you know what? Let's use this formula on 16 instead. What's 16 say? 16 is kind of nasty. But you going in the weird order. Okay. So first thing you need to find for me is the determinant. So the determinant of this 2x2 matrix would be diagonal 1, so negative 20 minus a negative 18. So that comes out to negative 2. Okay. So the inverse matrix to number 16, you start with taking what we know is the reciprocal of the determinant. So the reciprocal of negative 2 would be 1 over negative 2. And then you switch the order of the first diagonal. So the 5 will show up first and the negative 4 last. And then the other thing you change is you negate the values. So this 3 becomes a negative 3, and this negative 6 becomes a positive 6. So we're almost home free, guys. All you got to do now is treat this negative 1/2 like a scalar multiple and multiply it into all the terms. So this is a negative 5/2, and then it's a 3/2, and then it's a negative 3, and then it's a 2. So what you just found is called the inverse matrix. So what does the inverse matrix do? Well, you can't divide by a matrix because essentially a matrix is a function being applied to values. So you have to undo the matrix by using inverse matrices. So when you multiply two matrices together and they are inverses of each other, they create what's called the identity matrix. So what I'm going to do now, we're going to see that same question again. I'm going to show you the other method, okay? This is an alternative method. This is Hofbauer's favorite method. I know, I'm going to do it again with this other method. So we're not going to do 15 at all. You can just kind of use all that space over there. So we already know what the matrix is for the inverse, but let's pretend we don't. Here's what would happen, guys. You would multiply the original matrix by what you think the inverse matrix is, which I don't know what it is, pretend. But we're going to call it A, B, C, D. He's the inverse. And when you multiply two matrices together and they give you and they are inverses of each other, they produce what's called the identity matrix, which looks like this. 1, 0, 0, 1. Okay. They undo each other is what's happening. They're inverse operations essentially, but they're inverse functions to each other. All right, so here's what you're looking at, and you probably don't recognize this because you have hardly any experience with matrices, but you guys are looking at a series of systems of equations right now. So if I was to take the rows from this guy and the columns from this guy, I could set up two variable equations. You ready? This is getting kind of weird. So this row and this column is a negative 4a plus a 3c. And it is supposed to equal position 1, 1 on the identity matrix, which is a 1. Okay, stick with, now let's go to the second row and stick with the first column. So that's a negative 6a plus 5c. So row 2, column 1 is supposed to come out to an answer of 0, according to the identity matrix. That's one system of equations we'd have to solve. Put a pin in that for a minute. Now let's go look at the second column with the b and the d. First row, second column would be negative 4b plus 3d equals 0. And then second row, second column would be negative 6b plus 5d equals 1. So what you'd have to do here, guys, is you'd have to solve the systems, and then you would have A and B and C and D, and you'd be able to plunk them into this formula. I personally do not like this method.
Are you ever going to make us do this?
No.
Okay.
Never,
Miss
ever,
Pop
ever.
is insane.
She won't make their kid. No, we won't ever make you do inverse by hand at all, frankly.
No, I'm just saying, like, this being her favorite.
Oh, why is this? I think it's just the way she learned and she just stuck with it. She just really loves systems, you know? But guys, here's what I'm here to tell you. This little shortcut, which it is a shortcut, it's basically all of the algebra from this generalized. So you guys started to rattle off when I was writing down the blue one. You're like, oh, it's the same. Well, it's not quite the same, right? Because the 0 and the 1 are different. So if you generalize the steps in your math, what you create is a general formula. And in math, we call that a good old shortcut. Now, the trouble to using that inverse formula, if you ever have to do it by hand, is you have to remember it. So for a dyslexic, that's a problem sometimes. So sometimes I have to go and use the Hofbauer method because I can't remember my formula. Wah, wah. All right, so for your homework, you guys are doing selected problems off of worksheet 7. You should be completing your homework check through worksheet 7. So that includes worksheet 3, 4. Now you can complete worksheet 5 and 7.
It's such a review.